Welcome to Random Forest Algorithm. The random forest algorithm is a potent and simple learning method that constructs multiple decision trees, builds a collection or forest of multiple trees, each trained on a random subset of the data and features. Certainly, in the context of the random forest algorithm, let's use an analogy with the three decision models represented by coconut trees and apple trees. If we have three trees, one coconut tree, one apple tree, and another coconut tree, and their production are two coconut and one apple tree. So, the majority voting indicates that the final production is coconut.
To learn more, let's embark on a journey into this algorithm.
Let's make sure we're all on the same page with some key terms that will light up the path ahead. The first one is ensemble learning. Imagine a powerhouse team of algorithms working together to make predictions. That's ensemble learning. It combines the strength of multiple models for a more accurate and robust result. The second one is training data. This is the VIP guest list of our algorithmic party. Training data is what our model learns from. It's the set of examples used to train our random forest. The third one is forest. No, we're not talking about trees in the park. In random forest, a forest is a collection of decision trees, each contributing to the final prediction. The fourth one is overfitting. Think of it as wearing a suit that's too tight. Overfitting happens when model learns the training data too well, including the noise and the struggle with new or unseen data. The fifth one is classification. It's like playing matchmaker for data. Classification is when we categorize item into different group or classes. The sixth one is regression. When we're predicting a continuous outcome, like predicting the temperature of stock, prices, that's regression. It's all about finding the sweet spot to the number. The seventh one is future subset collection. Not all future get shine at once. Random forest randomly select a subset of future in order to each decision point, adding a touch of randomness to keep things interesting. Number 8 is bugging bootstrapping. Picture a party where guests are randomly choosing replacement. That's bugging bootstrapping. It helps create diverse subset of the training data for each decision tree. Number 9 is prediction. Prediction is the grand moment. After all the learning, our random forest get to make prediction on new or unseen data. Number 10 is majority voting. If democracy in action, for classification, the final decision is made based on the majority vote of decision trees. The more the merrier. Number 11 is classifier. Our algorithm, the hero of the story that classifies or predicts outcome based on the training data. The last one is veto voting. A unique twist, while not always used in random forests, veto voting allows some models to override others, adding an extra layer of decision making. Now that we're armed with these awesome terms, Let's venture into the enchanting world of random forests and see this concept come to life. Then, I'll explain how it works with visualizations. So, without delay, let's dive in. To kick off our exploration, we'll need a dataset. For this purpose, I've chosen a small dataset with 5 features and 6 rows of employee ID numbers, reflecting a real-world scenario. As observed, the target variable status only has 2 values, representing the contractual and regular status of an employee. This scenario is referred to as a binary classification problem. So, why do we call it random? Keep the question in the back of your mind. You'll receive the answer at the end of this video. Before we proceed, let me introduce to you the steps in random forest algorithm. Step 1. Select a subset of data points and features for each decision tree. Step 2. Build individual decision trees for each sample. Step 3. Each decision tree produced an output. And the last one, determine the final output through majority voting for classification or averaging the regression. The first steps involve constructing a new dataset from our original data. We randomly choose rows from the original data to create a new dataset. Each with the same number of rows as the original. Here is the first dataset, where I can only provide the employee IDs due to the space constraints. And take note that 2 and 5 appear more than once because we are performing a random sampling with replacement. The method we use to generate data is known as bootstrapping or bootstrap datasets. Now, let's train the decision tree independently in each bootstrap dataset. However, here's a twist. We won't use all features for training the trees. Instead, we'll randomly select a subset of features for each tree and exclusively use them for training. For instance, in the first case, we might use only features 0 and 1, followed by the features 2, 3, 2, 1, and 1, 4. Similarly, these are the subset that will be used for the remaining trees. Observe the difference in the faces of the trees compared to the others, and this is the random forest containing 4 trees. But how do we make predictions using this forest? We predict the output for each tree by asking whether a certain employee's status is contractual or regular. Now, we need to combine all the prediction because this is the classification problem. We'll use a majority voting. Clearly, regular is the winner since the random forest prediction is regular. So, in random forest, we initially perform bootstrapping, followed by aggregation, and in terminology, it's called bugging. So, in building a random forest, we follow these steps. Now, let's discuss a crucial aspect of this topic. Let's go back to our question. Why it is called random? The answer lies in the use of 2 random processes, bootstrapping and random feature selection. This approach combines bootstrapping and random feature selection for 2 main reasons. Bootstrapping ensures diverse data for each tree, reducing sensitivity to the original data, while random feature selection prevents high correlation among trees, avoiding shared decision nodes and behaviors that could lead to increased variance. These diverse ensure a balance where trees with differing predictions offset each other, contributing to overall result equilibrium. Now, let's dive into the algorithm assessment and wrap up our exploration. In accessing algorithm, we need the data set up. The actual labels contain predefined class labels, regular and contractual, representing real testing data. The predicted label list is populated by the performance random forest prediction method, which is a placeholder for the actual random forest prediction logic. This method returns a list of predicted label based on the random forest algorithm. In a real-world scenario, the logic inside perform random forest prediction would involve the random forest algorithm's prediction process, where it analyzes input data and produces prediction for each data point. However, in a given snippet, the method serves as a placeholder and the predicted labels are predefined. So, in performance evaluation, we have first the variables initialization. The first variable is total. Total represents the total number of data points in the evaluation. The second variable is correct. Tracks the number of correct predictions. The third one is true positive regular. Counts the instances where the model correctly predicted regular. The fourth one is false positive regular. Counts the number instances where the model incorrectly predicted regular when the actual label is different. So, actual regular is track the total number of instances where the actual label is regular. After the initialization of the variables, we have now in the loop process, loop truth data points. So, the code uses a loop to iterate through each data point in the evaluation. Next is prediction check. So, it checks if the prediction is correct by comparing the actual and predicted labels. If they match, it increments the correct counter. Calculation. After looping through all data points, the code calculates key performance metrics. The accuracy is the proportion of the correct prediction. The precision is the precision of the regular class. The recall is the recall or the sensitivity for the regular class. So the F1 score is, which is a balance of precision and the recall for the regular class. So, accuracy represents the proportion of correct prediction in the entire dataset. With a provided numerical value of 0.8333, 83.33% signifies that 83.33% of all predictions made by the model are correct. These metrics reflect the overall correctness of the random forest model on your dataset. Precision. Precision for the regular class is a proportion of correct predicted regular instances out of all instances predicted as regular and contractual, with a numerical value of 0.67 or 67% indicates that 67 of the instances predicted as regular by the model are genuinely regular. This provided insight in the model precision and identified the regular class with exactness. Recall. Recall or sensitivity for the regular class is the proportion of the true regular instances identified by the model, with a numerical value of 0.67 or 67% indicates that the model successfully identified 67% of the true regular instances. This metric gauged the model ability to capture all true regular cases. So F1 score for the regular class is balance measured between precision and recall. The numerical value of 0.67 implies that this is the result of balancing precision and recall. This provides a combined measure of the model's significance in identifying the regular class. As we wrap out Random Forest discussion, wishing you algorithmic adventures filled with success and joy. Happy exploring!